page of our packet for the momentum unit deals with collisions in 2D. So we're going to look at some inelastic collisions that have both x and y components. Now the rules are going to be the same. You still have to conserve your momentum. So whatever momentum you had before a collision, you have to have the same amount after a collision. And same rules apply in terms of inelastic collisions. They tend to stick together, and kinetic energy is not conserved, but momentum is. So for the case of inelastic collisions, we're going to be specifically using the law of conservation of momentum, not so much the law of conservation of energy. Now this is a simulation from the PHET website, phet.colorado.edu. Has a tremendous amount of excellent simulations. All right, let's do a 2D problem. The key concepts for this section are going to be that the sum of all of our x momenta initial is going to equal the sum of all of our x momenta final. And likewise, in the y direction, the sum of all of our y momenta initial is equal to the sum of all of our y momenta final. So in this problem, a radioactive nucleus at rest decays into a second nucleus, an electron and a neutrino. The electron and the neutrino are emitted at right angles and have a momenta of 9.3 times 10 to the negative 23rd kilogram meters per second and 5.4 times 10 to the negative 23rd kilogram meters per second, respectively. The question asks, what are the magnitude and direction of the momentum of the second recoiling nuclei? So, let's do a before and after picture. Now in the before picture, everything's together, right? One big happy club, one big happy family. And afterwards, they're going to break apart. And it says that an electron is emitted at a right angle from a neutrino. So let's draw the electron in blue this way. So this electron is going to have some momentum. We're going to call it rho sub e for the momentum of electron. Also, we're going to have a neutrino, make that green, and that's going to have some momentum at a right angle. So when we choose our coordinates, let's choose coordinates that are going to be easy. Since they're at a right angle, we might as well make them in the xy plane. And that's going to have the momenta of the neutrino. Lastly, you're going to have a remaining nuclei. Now this thing, it's got to compensate for the fact that we had 0 total momentum in the x direction and 0 total momentum in the y direction. So it's going to have to counterbalance what the electron did by providing some x momentum, and then also going to have to counterbalance what the neutrino does in the y direction. So it's going to have momenta in the upper left direction, so negative x and positive y direction. And that'll be at some angle theta, which you'll figure out later. And that'll have some momentum of the nuclei. I'm just going to put NUC for nuclei. So let's break it apart into the sum of all of our x momenta and the sum of all of our y momenta. Initial equals 1. So 0, really, right? Initial momentum 0 is going to equal your final momentum, which is in the x direction. You're going to have momentum of the electron minus, I'm going to call this, watch the notation here, it's the x component of the remaining nucleus. That's this component here. And likewise, we might as well finish this off and say that the momentum of the nucleus in the x direction is equal to the momentum of the electron. And likewise, in the y direction, we can make a similar statement. So 0 is going to be equal to the momentum of both the neutrino, so rho neutrino, plus the y component of the remaining nucleus. And they're in opposite directions. We define up as positive, so that means in our picture the neutrino has a downward momentum, and I'll make that green so you guys know which one that is from the picture. And likewise, we'll identify our electrons' momentum so you can identify with the picture. Alright, so in our picture over here, in our diagram, we want to know the magnitude and direction of the momentum of the remaining nuclei. So let's find that out. We can use this right triangle constructed by the x and the y components of the momenta of the nuclei, or the remaining nucleus, to get the magnitude. So then I can say from our picture that the total momentum, the magnitude, is going to equal to, and this is by the Pythagorean theorem, the x component of the nucleus momentum squared plus the y component of the nucleus momentum squared final. And we know from these previous equations what exactly those x and y components are. So really we're saying that the momenta of the nucleus is the square root of the momentum of the electron squared plus the momentum of the neutrino squared. So that's 5.4 times 10 to the negative 24th kilogram meters per second squared plus the momenta of the neutrino. I'm going to run out of room, but the value there was 9.3 times 10 to the negative 23rd kilogram meters per second squared. And when we do the math on that, we should get a value of, looks like 1.08 times 10 to the negative 22nd kilogram meters per second. So that gives us the magnitude of the momentum of the nuclei. Now the other piece, the angle, well, we can just use simple trig for that. Running out of space, but let's do, looks like we have opposite and adjacent. Opposite would actually be this y component, which was the neutrino, the same as the neutrino, and the x component is the same as the momenta of the electron. So what you can say for theta down here is that theta is going to be the inverse tangent of the momenta of the neutrino divided by the momenta of the electron. And again, I ran out of space, but that should be 59.9 degrees. Let's calculate that. And that's how we do things in 2D. You got to split up your x and your y, and you apply the law of conservation of momentum in both the x and the y direction. Your solution for momenta of the nucleus is 1.08 times 10 to the negative 22nd, and your solution for the angle at which that was happening, this angle right here, should be 59.9 degrees once you do the inverse tangent. Okay, try one on your own.